So like I said, an acid, when you add it to water, you're gonna get a hydronium ion. And a base, when you add it to water, you're gonna get a hydroxide ion, which is OH minus. And then there's sorry. Let me just look for that name before like I say it wrong again. So arenas acid. Yeah, Bronsted-Lowry. So basically what Bronsted and Lowry found out was that an acid will donate a proton in the reaction, and a base will accept a proton. So every time you hear the word proton, that's just it's it's a positive hydrogen ion. So according to Bronsted-Lowry, an acid is a proton donor and a base is a proton acceptor. But to be honest, like if you look at it, that's basically what Arrhenius discovered. But with Arrhenius, he used water, because if you look at it, let's say HCl plus water, that's gonna give you H3O, 3O plus Cl. So if you look at it, this proton, it's gonna move, it's gonna split from the from the from the from the from the hydrochloric acid, and it's gonna act with the water, giving you a hydronium ion, and the chlorine is gonna be left alone. And when it comes to a base, let's just say it reacts with NaOH. So that's gonna be plus water. So basically, in this particular case, this proton is gonna move from the water to the sodium hydroxide. So you're gonna have something, so NaOH2 plus OH minus. But this, nah, let's just leave it like that. So I'm pretty sure you understand that now.
Yes, sir.
So I suggest that every time you see an acid-base reaction, you should probably remember the Bronsted-Lowry acid and base definition, because I think it's gonna be the one that's gonna be most useful in identifying the conjugate acid base pairs, because you can just identify that this proton moved from here to there, and this proton got accepted from here to there. So here we have an example of an acid-base reaction in the Bronsted-Lowry definition. So that's hydrochloric acid added to ammonia, which is gonna produce ammonium and chlorine. The chlorine is now alone, so they're both ions. So I think we can go to the next definition. So so I'm I'm pretty sure you guys are aware of amphoteric substances which can actually act as both an acid and a base depending on the conditions of the reaction. And an amphiprotic, that means it is able to donate a proton and accept a proton depending on the conditions of the reaction. So here they're just gonna give you some few definitions of when a molecule has only one proton, it is called monoprotic. Two electrons, diprotic, and more than that, it becomes poly. So I think this is the part that you might find difficult most of the time, where they're gonna talk about conjugate acid-base pairs. So let me just do this now. So if you look at this proton is gonna move to here. So from the looks of it, the hydrochloric acid is gonna split into chlorine and a proton, and the ammonia is now gonna have a proton added to it in order to form ammonium. So this is a base in the forward reaction, and this is the acid in the forward reaction. But since this reaction is in equilibrium, there also has to be a base and an acid this side in order for the reaction to be reversed. Because when the reaction is in equilibrium, that means the forward reaction and the reverse reaction are actually occurring at the same rate. So it's basically like physically you can't see what's happening, but on a molecular scale, the products are becoming the reactants, and the reactants are becoming the products simultaneously. So if you look at it, this is now gonna have to be our base, sorry, our acid, and this is our base. So that means this base turns into this acid, and this acid is gonna turn into this base. So those are the conjugate acid-base pairs. The base turns into this acid, and this acid turns into this base with the forward and reverse reactions. So that's how you're gonna identify the conjugate acid-base pairs. You understand that part?
Yes, sir.
Okay. Because I think, yeah, like even here they wrote it like this. So I think after the conjugate acid-base pairs, what comes up next? So now we're gonna discuss the strong and weak acids and bases. So um from what we know, the strong acids and bases they're gonna completely dissociate when they are put into a solution. So that means so that means they have a larger percentage of moles when they're added to water. And so basically, when they're added to water, the concentration is going to be very high because they have a large percentage of moles. And when it comes to weak acids and bases, they partially dissociate. So that means their concentration is going to be the concentration of that water is going to be lower, and the percentage of moles is going to be how do I say it, smaller. So basically, these arrows here, they just show that there's little ionization, and this one shows that there's complete ionization. So I don't think they're gonna ask you guys to show using these to show by using these arrows whether a reaction is using a weak acid or or a strong base. So basically, I just suggest that you familiarize yourself with the list of strong acids and strong bases. From what I can tell you, HF. Uh, let me just leave this one alone. Like up here, you know that hydrochloric acid is a strong acid, nitric acid is strong, and sulfuric acid. And you know, sodium hydroxide and potassium hydroxide are strong bases. So you just need to like familiarize yourself with some of the weaker and stronger acids and bases. So now they say dilute and concentrated solutions. So we know that when something is dilute, that means they probably used a weaker acid or a weaker base. And when something is concentrated, that means the concentration of the acid and the base is high, meaning that they used a stronger acid or a stronger base. So here, I'm not sure if they're gonna want they're gonna ask you guys for these definitions, but they say a standard solution is a solution where the exact concentration of the solute in the solvent is known. So a standard solution, that just means the concentration of in this particular case, when they say the solute, we're gonna say an acid or a base, and the solvent, that's gonna be our water. So a standard solution, that's a solution where the concentration of the acid in that water or the concentration of the base in that water is known. So a concentrated solution is a solution where there is a high ratio of dissolved substance. So basically, a concentrated solution, that's where the the concentration of the solute, or let's say the concentration of the acid or the concentration of the base outweighs the concentration, or let's say overpowers the concentration of the water. or let me just use sugar. So basically, let's say you want to make starch water, right? So you're gonna have your water, and you're gonna pour maybe like a little bit of sugar. You just have like two spoons of sugar. Now this is dilute because you barely taste the sugar. But once you keep adding more and more sugar, it's gonna become more and more concentrated to the point in which you actually you when you're drinking the water, you can barely taste that it's water. All you taste is the sugar. So I think that's a nice way of looking at it. So here is a summary of the properties. So we're gonna have our acid and our base. So with a strong acid, there's a high percentage of there's a high percentage of ions in the solution. With a weak acid, there's a small percentage of ions in the solution. In a concentrated solution, there's a large number of moles of the acid. And in a dilute solution, there's a small number of moles of the acid. Same applies to the bases. So these are just some questions. So now we're gonna come to the ionization constant and dissociation constant. So the equilibrium these constants, they help you to determine whether the acid that is used is strong or it's weak. So from this, you know that um, from the from chemical equilibrium, you know that the equilibrium constant Kc is the products divided by the reactants. Well, that's the same situation here because um the ionization constant, which is going to be our Ka, it's basically in this equation this is our only product, because if you remember from Kc, only gases and aqueous molecules are considered when measuring Kc. So that means the water, which is a liquid or something that is solid, it's going to be disregarded. So you're going to have your products divided by the reactants. So these are going to be your products, and this is your only reactant that's going to be considered. So that's going to be your ionization constant. And this is going to be your ionization constant when it's a weak acid. So basically here they're going to give you guys the value of the ionization constant if it's a strong acid. So you just know that the ionization constant is going to be high, around like around 10 to the exponent 9 high. And when it goes down to like decimals, that's when you know that your acid is weak. So basically here is 10 to the exponent -5, and here is 10 to the exponent 9. So basically you can just do this for a strong acid. For strong, your ionization constant is most likely gonna be greater or equal to 1. And when it's weak, the ionization constant might be, it's most likely gonna be less than 1. So I think that's it. And I think, and same applies to bases. But I don't think they're gonna ask you guys that many questions about Ka and Kb in the in the test and in the exams. So now we're gonna go to the acid base reactions. Honestly, this chapter requires a lot of study, because there's a lot of different ways in which acids and bases react, and there's a lot of different products that can be formed. So let me just